All right, here we're going to introduce scatter plots into our linear models. So basically scatter plots are plotting of points, right? Ordered pairs, an X and a Y, to represent actual data over time. So you can use a scatter plot to kind of show trends, whether things are increasing, decreasing, and that's kind of what we're going to look at in this video. All right, so I apologize for this picture. For some reason, it just wouldn't take very nicely, but you know what, it is what it is. So we are showing population of butterflies. Let's make them butterflies because why not? And obviously these are years since 1980. Now, one thing to notice, our x-axis does not start at 0. Our x-axis starts at 1975. That means if we were going to find for the year 1992, for x we would type in 1992. We would not use let x equals 0 somewhere because the way our model is presented, we are using the years as given. Okay, so in this first, we're going to start with what is the slope. Well, looking at the information given, our slope for this particular problem is 21.713. Now, we can make that a fraction by putting it over 1. So there's our slope. Now, when we're interpreting this, think about what those values mean. The top number is the y values. Y values are the butterfly population. The x values are the years since 1980, because that's when our first piece of data happens. So when we're talking about our interpretation, the butterfly population, the butt pop, increased. Now I know it's an increase because this is positive. Increased 21.713 per year after 1980. Right? Because it's per 1 year after 1980. So using these labels so that you know what your y's represent, what your x's represent, that helps with the information. What's the scope of this model? Okay, that's a new word. So a scope of the model is your range of x values given on the table. And so when you look at this, you can see that my graph only goes from here to here, right? That's the actual line. But these are outside the given line, but they're pretty close, right? 5 years on this side, and I don't know, maybe 3 years on this side. So this scope of the model would be from 1975 to 2005. The scope is the range of x values that it would be okay to think about, right? It wouldn't make sense to say, you know what, let's predict the butterfly population for, 1900 using this model. So much has changed since 1900 that would have affected the population. This butterfly might not even have been around in 1900. We don't know. So you can't go either way. And we can't use it to say, well, let's check out the year 3000. How many butterflies will we have? Who knows? There could be a meteor and we could go back to all being dinosaurs by the year 3000. Nobody knows. So the scope is the range of x values that are close on either side of the given data. What's the linear correlation coefficient? And interpret this. Now, okay. R squared is how we're going to get this. So the linear correlation coefficient is actually determined by R. And what this is, it tells you the fitness of your line in terms of how close to your data is your line. So the more linear your data, right? These dots are my data points, and you can see they're all fairly close to the line. We've got this one out here that's kind of its own beast, but the rest of them are pretty close to the line. So with linear correlation coefficients, the closer you are to 1, the more linear your correlation is. If you have a linear correlation of 0.1, well, that just means you have a lot of random data. Okay? And you also need to be sure R squared, it's always squared, that's always going to be positive. When you take the square root of that, it's always going to be positive. So you do need to look at your line. In this case, our line is going up, that's positive, so my R value will be positive. However, if our graph, if we had a graph and our line was going this direction, our R value would be negative because it's going down. So you do have to pay attention to the slope of your line. Whatever your slope is, if your slope is positive, your linear correlation coefficient is going to be positive. If your slope is negative, your linear correlation coefficient is going to be negative. Okay, with all of that being said, if I have an r squared value of 0.8116 and I want to find the linear correlation coefficient, I need to unsquare this, right? We also talk about that as being square root. So it's an equation. Do the same thing to both sides. So I'm going to take the square root of both sides. So the square root of r squared is r. The square root of 0.8116 is 0.9009. Now, if you have a linear correlation coefficient 0.9 or above, that's pretty good. I mean, you're getting closer to 1. So I would say there is a strong positive, I know it's positive, it's going up, strong positive linear correlation between the butterfly population and years since 1980. Okay. Positive correlation does not imply a causation. The fact that time has passed and years since 1980 have occurred, that's not what caused the butterfly population to grow, right? It could be all sorts of things. People might have created butterfly sanctuaries where they're breeding butterflies. We don't know. Too many other things could be causing this population explosion. It has nothing to do with the years, right? So correlation does not imply causation. That's a good thing to know. All right. Use the model to estimate for 2000 and then compare. How does this estimate compare to the actual for 2000? So when I'm looking at my model, I've got y equals 21.713. I'm using the year 2000 for x. Oops, forgot a 0. And then I subtract 42,853. When I type that into my handy dandy calculator, which I am doing as we speak, we end up with 573. So for 2000, which is right on this dot, our estimate, which is right here, estimates that to be 573. Now the actual, if you recall, is right here, because the dots are the actual. So, I mean, I could, if I had, it looks like it's pretty close to 500, we could say the estimate, the line is the estimate, right? Very little things, very few things in life are actually linear, that go in a nice straight line. But linear models are one thing that do. So we could say that the model estimates approximately 70 more butterflies for the year 2000 than the actual. Or if you don't know the value, I mean, we don't know for sure that this is at 500, you could simply say the model overestimates for the year 2000 because the actual, we know the actual is less. The actual is less than the estimate because the dot is below the line. Right? If we had been for year 1996, it's very easy to see that the actual is way higher than the estimate because that dot is above the line. So it all depends on the position of the dot compared to the line. And the last question here, I believe, should this model be used to estimate the population for 2030? Well, here's 2010, 15, 20, 30 is not even on here. No. We would say that is outside the scope. Oops, forgot to see, scope of the model. So it's just not close enough. You could use this for 2005, that would be fine. And even if you wanted to go backwards and say, what did you think it was in 1975? That would be fine. But using 2030, nah, that's too far out. Too many things could happen that could change the butterfly population. And that's it.